So should I start it right, like, or they're going to give me a signal, or should I just start it? Starts at 150. That's the reason I'm asking. Which is 1 minute from now. So. Sure. Thanks. Oh, sure. You got it. Okay. Hello. 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 Okay. Ready to rock? Yeah. Okay. Cool. Hello, everybody. Welcome to Spark in Production, lessons from 100 plus production users. This is Aaron Davidson. He's a Spark committer and also Databricks team lead. Please leave your questions to near the end. We'll be running around with this microphone so you can ask your questions. And without ado, Aaron.
Hello, everyone. I'm Aaron, and I'll be talking today about Spark in production, sort of our lessons at Databricks from over 300 production customers. So it's relevant to this talk, so I'm going to briefly discuss about Databricks. You might have already seen Hosein's demo, but Databricks is founded by the creators of Spark and remains the largest contributor. And our main sort of product is this hosted service, which features Spark on EC2, with some sort of nice like UX experience stuff, user experience things like notebooks and plot visualizations, and some nice sort of like management of Spark clusters things, for instance, the cluster management and scheduled jobs. So as a hosted service running on EC2 with a focus on Spark, we get a lot of very high information user feedback about Spark. A customer may come to us with a problem saying, oh, this thing runs slow, or it doesn't run at all, and they give us permission to look at sort of their notebook, and they give us permission to maybe modify it and run it. And so we get a very high-touch information about like their workloads and what they're doing wrong and what they're trying to do. And of course, we also get just as much information from the community, from summits like this and from the Spark user list. So this information is kind of intermingled together at this point, but I'll present on it as a whole. I'm going to focus on two main types of lessons that we've learned. The first type is lessons for Spark. And so these are like kinds of problems which are so common or so fundamental that they have to be solved in the Spark layer. And so for these kinds of problems, I'll be mainly discussing them for context so that you guys can understand sort of where Spark is going and why, and what kind of problems we're trying to solve. And for the second type is lessons for users. So this is if you have a specific problem that we discuss, potentially you can pull down some lessons from that and use it in your own thing. Or if you're thinking about using Python or something like that, it might be useful. OK, so the talk is going to be structured with three main problems, which I'll talk about the context, what the problems are, and what the sort of current thought about the solutions are. And so these problems are moving beyond Python performance, using Spark with new languages focused on R, and network and CPU-bound workloads. And at the end, if we have some time, I'll talk about a couple miscellaneous pitfalls, which sort of, as I made this talk, I sort of gathered together. But if I don't get time, it'll be on the slides. And so the point is that if you are using one of these things, then maybe there will be like a lesson that you can directly use for your work. But even if you're not, what I hope is that you'll still be able to gain some sort of context, more information about Spark as a whole, maybe a component you weren't very familiar with, and also know like where certain pieces fit together. OK, so how popular is Python? It was a question that we asked on the Spark survey. And what we saw was pretty interesting. So if you know Spark's history, about 1 to 2 years ago, Python was very much a second-class citizen in Spark. It was a lot of the APIs were sort of not quite up to par with the RDD Java and Scala APIs. And the performance, there were obvious problems with it, like very, very obvious things that we could fix. So today, as of the 2015 survey, 71% of Spark users use Scala, and 58% use Python. Obviously, these are not disjoint people. We also see that Python has grown the most since 2014. OK, so a lot of new people are coming to Python, are finding it to be a very useful paradigm. To talk more about the problems that we see in PySpark, I would like to very briefly introduce the architecture. So here is the simplest possible Spark program, or almost simplest, where we read a file from Hadoop, from data, and we filter it by a string. So we filter out all strings that contain the word foobar, and we just count these up. Okay. So this is the diagram from the PySpark about page. And so let's briefly deconstruct it. It's actually not so bad. So on the very left-hand side, we have the Python Spark context. So this is what you're typing into. You're saying sc.text file. And then a little bit to the right of it, we have the Java equivalent, which the Python one will communicate with the Java one, and will say, OK, here's the user wants to have this RDD and that RDD and to count it. OK. And then once you've entered all this in, the Java Spark context will talk to the right-hand side, which is your cluster. And these are Spark workers, more commonly called executors now. So these are Spark executors which get the tasks, and then we'll do some of the work in the JVM and some of the work in Python. So the first question is, which of this work is going to be done in Python? So if we look at what we're asking Spark to do, first we say, grab some data from HDFS, from Hadoop, and split it by line. So is this going to operate in Python? Well, it could, but the library we're using is actually the Hadoop input format, which is written in Java. So this part will be running in the JVM. It knows how to connect to Hadoop, how to pull files, split them, and read lines. The second part, the filter, has a Python lambda in it. So unless we're doing something super fancy, such as compiling this Python to LLVM, this is definitely going to run in a Python interpreter. And the final one, the count, could be run in either one. Okay. But if we look at it from this perspective, if we didn't have the filter, note that we could do both of these operations, the text file and count, without involving Python, right? But it's actually very rare in Python or in RDD interface that you get to do this. Because unless you want to do only counts of data files, you pretty much have to have code. And so you must have Python or Spark code. OK, so much more commonly, we'll have some Python code. This is obviously the simplest possible example. OK, so how does this run? Well, if we imagine we have some mysterious data, which maybe is an HDFS or an S3 or something, well, as I said, the data will be read in by these Spark JVMs. It will be then sent over a pipe, actually a socket, to the Python. This is where we convert from Java objects to Python objects via pickling. And then the Python will do the filtering, will run its Lambda over every object, and pass it back through the pipe back to the JVM. The JVM will do this aggregation and send it to the driver. OK. And so the problem here is actually the Java to Python communication. This is expensive. It's inherently expensive. And this problem about this expense, this extra thing we have to do when we use Python, is sort of a fundamental problem of this architecture, is that converting from arbitrary Java objects to arbitrary Python objects and back will always be expensive. So we need sort of a dramatic change in how we do this in order for us to see a much better performance from Python. And so what is actually the problem with this? So we see, this is an example. If you saw Michael's earlier talk, this is actually the same average example. And we see here a pretty typical result, which is that Scala runs in 4 seconds, and Python, an equivalent program, runs in 9 seconds. So this is, of course, a single example, but it's definitely not atypical in what we see in actual differences in workload performance. So how do we move beyond this? How do we get much better? Well, if you also saw Michael's talk, you'll know that the answer is to use data frames. So in this case, you can imagine using data frames in this way as the equivalent to saying sc.textfile.count. So where we told Spark everything what it needs to happen, and it could all happen in the JVM, here we've done the same thing, but we've used higher level, more expressive primitives. So we've told Spark, oh, you should group by, you should aggregate this column into averages, and then collect it back. And then so actually nothing here is going through Python in this situation. And so we see, of course, the same performance in all languages. All right. So that's good. So moving on to sort of Spark in other languages, one thing we see is as big data becomes more prevalent, new people want to sort of use the paradigms they know and understand on bigger amounts of data. And the example we'll be using here is R, which is a very common one. So this is a statistical programming language, which has a somewhat different paradigm than you see in Python or Java. And people are very good at doing analyses and plotting and such with R, but they may not know distributed computing. And so we see, say, 2 groups of people who have never used Hadoop or maybe never used distributed computing, and we see people who are familiar with statistical languages. And actually, the intersection of those is actually relatively large. These are statisticians. Sometimes these are called data scientists, although, of course, that definition transcends human definition. So I will not even assert that even half of all such people are called data scientists. But there is quite a large group of people who are fit in this category. The problem is it's difficult to run an R program on a cluster. It's just technically challenging to rewrite these algorithms. There's some very advanced algorithms in R, and to rewrite them is very hard because they make assumptions about shared memory and things like this. And there was actually a project at UC Berkeley to do just this. But it turns out it's very complicated and it's hard to generalize. And if you wanted to sort of do it yourself, if you wanted to take an algorithm and distribute it, well, the paradigm shift it takes to go from a single node algorithm to a multi-node algorithm is significantly harder, significantly larger shift than it takes to change between languages. And so the idea is that you might as well use Java or Python if you can represent this algorithm simpler than to keep with R. And so we've seen sort of a pattern emerging, which is to do the distributed computation initially, so do some transformations in Scala and Python. And then you bring back a smaller data set on the order of megabytes or maybe a few gigabytes to a single node to do quick plotting and analyses in R. And so the result is that today the SparkR interface, the interface to R from Spark, or maybe the other way around, is data frames. And so this is an example of, OK, it looks much like the SQL data frames. Of course, data frames originated in R, so this is a very familiar paradigm. So we read a data frame as JSON, we do some filtering, and we can just use it. OK. And so the idea is that we can express our stuff in data frames, and if you needed to use a UDF, that UDF would be written in Scala or Python or Java. OK. And if you want to see more about this particular component, there's a talk by Hossein tomorrow about enabling exploratory data science with SparkR. OK, there's also our documentation. All right, so the final component I wanted to talk about was network and CPU-bound workloads. So what we mean by network-bound workloads means something a little bit different in Databricks than it does in a traditional data warehouse. And this is because Databricks uses S3 very heavily as a replacement for HDFS. So S3, if you don't know it, is a key value store. It's a blob storage in the cloud. So it's provided by Amazon. You don't run anything. So it's completely accessed over the network. It's intended for large objects. And to give you some properties, it has about a 10 to 200 millisecond latency for reads and writes, so which is pretty long for individual operations. There exist adapters for HDFS-like access called S3N and S3A. That's the newer one. So you can access it like HDFS. You can do sc.txt file, this sort of thing. And there's some confusion about this, but it turns out it actually has pretty strong consistency guarantees for many common workloads, such as adding new data. And there's some caveats about, you can't delete data, and US East 1 has some side note. But otherwise, it does have strong consistency. And such a key value system like this does tend to exist in basically every cloud provider. Like Google has one, Azure has one, all this kind of thing. So this is not an uncommon pattern. And to give a little bit more color, literally color, to the picture, a traditional warehouse may have might have an instance or machine, and on this machine there's the executor JVM, as we all know and love in Spark, and there might be HDFS, and then we have the same sort of thing copy-pasted in multiple places. So in Databricks, we have the executor JVM, and instead of HDFS, we get our data from S3. And the reason we do this is because we want to have complete elasticity of our instances. We want to be able to put them up and down based on the compute, based on if you have a job running, do we need instances? All right, so HDFS doesn't really work for us because it doesn't deal well with losing a lot of nodes, or potentially all of your nodes. You would lose data. Okay, and so we have a corresponding cache. We have to use our disk for something, so we have implemented a way to bring S3 down and cache it locally to utilize those disks. But sort of this is not the default. By default, you go straight to the JVM. OK. So for those of you who want to use S3N, for instance, we found originally we couldn't quite get the performance that we expected just out of the box. We were unable, and so before I go further with this part, I'd like to point out that our experience, this is very much your mileage may vary. I would do benchmarks on your own, and if you find the same set of things are occurring, then you sort of maybe follow the same pattern. But it's also possible that you get perfectly good performance out of S3N due to where you're executing and where your data is and all that stuff. So, but for us, our experiences were, we were unable with the default S3N to saturate a 1 gigabit network using 8 threads on 8 cores. if we oversubscribe, the number of threads, if we use 16 or 32 threads, we actually became CPU bound, which is kind of strange for an I/O job. But we peaked at around 800% CPU utilization and only 100 megabytes, which isn't quite 1 gigabit. So we investigated this, and we found 2 performance problems. So the first one, if you see code like this, which is saying, please attempt to fill a 256 kilobyte by reading from a stream, if you're familiar with this API, it's allowed to read fewer bytes than this, and it will return those bytes. And so the question is sort of, what does numRead tend to be? So we saw a very strange pattern, and it seemed to be the case. And I even tried it again yesterday to make sure, because it's very strange. But what we saw was that numRead alternates between reading 8,999 bytes and 1 byte, and back and forth. And this is sort of at the lowest level of the S3N library. This is happening, and it also happens for S3A, so it's pretty weird. But that said, this is what we saw. And this is kind of expensive, because if you go through many layers of stack, basically, to read the next bytes, you expect approximately 256 kilobytes, but you get back 9, then you do make this call a lot more often than you might have expected, and you might have a lot more CPU overhead. And it's especially bad if you go back all the way down the stack trace and you get 1. You expend a lot of CPU if you're only getting 1 byte every time you go read. There's a lot of objects that are wrapped around each other. So there's an obvious answer to this one, which is buffering, which is buffer 128 kilobytes or 256 kilobytes before sending it up to the higher level. So that's pretty straightforward. So buffer at the lowest level, and you can avoid this huge call stack. The more interesting problem was actually our second problem we encountered, which, if we imagine this very similar computation, reading a text file and doing an expensive computation over it, then in time what we see is that we might read a buffered 128 kilobytes. We perform the computation over that 120 kilobytes. We read it, and then we repeatedly. And so that seems pretty reasonable. But if you look at sort of the resource utilization over time, you notice that, of course, you first start using the network, and then because you're no longer reading, you're no longer using the network. And then you do computation, and then you do network and computation. And you see that we have 2 resources which we could use concurrently, but we're only using 1. And of course, in practice, it isn't this stark. It's not this bad, because you have 8 cores. But we did definitely see a lot of going up and down, and we were unable to achieve sort of maximum throughput, even with the first solution. So to fix this, we picked a pretty well-known solution, which is pipelining. So here are 2 abstract representations of threads, which you can tell by the very beautifully drawn squiggly line. And there's one thread whose job it is to read from S3 and fill a pipe or a buffer. And in the user program, when it comes and asks for data, if there's data in the pipe, it takes it. Otherwise, it will block waiting for more data to arrive. OK. And so this kind of looks like you read some data, and then as soon as you finish reading, you start the computation. And while that's going on, you might read some more data. Computation's still going, so you read some more data. And then the computation takes the first one, you read. But here, the computation is going pretty slow. So the read will actually, you can't do another read until it's drained the buffers. So eventually the computation finishes, and the read continues. And basically, what we see is that the computation is always occurring. So your slowest resource is always being utilized, which is pretty good. So this is the optimal situation here is if both of them are the same speed, and then you get they're both always operating. So that's a 2x improvement. And sort of the worst case scenario is if one of them is super fast, then you're really not getting anything from this. And so that's where sort of maybe common wisdom might be different here. Because common wisdom might say that, your computation is probably much faster than what your network throughput or your disk bandwidth or something. But it turns out in this case that very often the computation was not a lot slower. It was actually the same order of magnitude as the reading. And so this got us a huge win. And so in our case, we were able to saturate it's a little bit puny, it's 1 gigabit network, but saturate a 1 gigabit or 10 gigabit network in this case. And it used 100% of a core. So across 8 threads, it utilized one core. And this was largely, in inspection, it was largely due to SSL overheads, which, if you think about it, is kind of strange, because you expect symmetric key encryption to be pretty fast. It should be hardware accelerated, but whatever. We stopped investigating at this point. So with this optimization, we found S3 to work pretty well. So Spark hides the latency. So one of the big problems with S3 is the latency, and Spark hides this. So you don't really see 100 millisecond latency if it only happens once per task, because all the tasks are happening in parallel, and there's a lot of them. And they only maybe need to do one read, because you have like a one block or something per task. The one place where this hit us is actually on the driver side. So Spark has to do lookups to find all of the files before it starts a job. And what you may know is that it does this in serial. And so this is typically not a problem unless you have partitioned data. So you might have like one folder per day or something. And in this case, which is pretty common, you might have like 1,000 files, 1,000 folders, and then to list each one individually at 100 milliseconds starts to be very expensive. Okay, so that's the one problem that we still have with S3. And in our experience, network is pretty fast. And that's kind of a funny statement, because pretty fast is relative. So you might ask, why is network pretty fast? How can it be considered pretty fast? It's like slow, right? So if we look at our R3 2x large that we typically use, we see that it has 120 megabyte network. That's a 1 gigabit. It has a single 250 megabyte disk. And so you could see that you could get a maximum 2x improvement even though we only have one disk, which is nothing to scoff at. That's pretty good. But in fact, in practice, we were unable to realize this gain. We could get these speeds if we did them sort of just a read test. But on our actual workloads, we got a very negligible increase, or some small increase, but very rarely do we see a full 2x. And so the surprising result of this is that actually it's not memory or disk that many workloads are actually blocked on. It's actually CPU. And so I might go so far as to say most workloads that we investigated into were actually CPU bound on the read side. And one of the main ones here was actually TPCDS, where almost every one of the queries was CPU bound. And so why is Spark often CPU bound? Well, the first people I'm going to blame is you guys. It's your fault. Users tend to think more about the high-level details than CPU efficiency. So is this a problem? Well, I mean, not really. This is pretty reasonable. So as my colleague Reynold Shin would say, going from not working to working is the biggest performance improvement you'll ever see. So spending your time trying to express your thing rather than make it fast is pretty reasonable. For instance, if you have a problem which is like, I need to find this string pattern within this bigger string, and you decide to use regular expression library, well, maybe you'll just use the default Java one because it's there and fast, fast to get started with, rather than trying to find like the most efficient regex library, or rather than writing a finite state machine. So that's cool. So all we need then is tracing and visualization tools to sort of find, when efficiency becomes the problem, when performance becomes the problem, we need to be able to identify which part of our computation was the bottleneck. So we find that, oh, this regular expression stage, this is actually what's slow. This is what I need to make faster. And for this, I'll point you to Andrew's talk tomorrow, which is on Spark UI visualization, a lens into your application is the name. So he goes into detail about the ones that Spark provides out of the box for visualization. Additionally, users need to be provided with efficient primitives for the common operations. For example, in Spark SQL, they actually do have a faster regular expression library, which they pulled from somewhere else. And they also even have a faster string library, which I think Michael mentioned. So by providing these efficient primitives, you can still express your code in the way you want and get better speed up. And this is also one of the motivations for Tungsten. So we spend a lot of time optimizing the data frame operations so that because they're generalizable, you can get fast ones. Other than sort of being your fault, or at the user level, just reading data is actually surprisingly expensive. So one obvious one is decompression. So there are three pretty common compression algorithms: Snappy, LZO/LZF, and gzip. And between these, Snappy is sort of the highest bandwidth, lowest. So it can compress the most, but it does the least compression ratio, so the size is about the same. And LZF and LZO is in the middle, and gzip is sort of the highest, lowest bandwidth, highest compression ratio. So it takes a lot of time, but it compresses more. So in our experience, one should be probably pretty wary of gzip, because in almost any case that you use it, it ends up being a CPU-bound workload on the read side. So I might recommend LZF or LZO in a general case, but of course, this is very much prone to benchmarking. This one's actually one of the harder ones, because you sort of have to know at write time what the read side is going to be bound on, and you may not have a feedback loop. If you, after a while, you say, wait a minute, we actually should have used a different compression algorithm. But even when compression is not the problem, sometimes just turning bytes into Java objects is the problem. And so that is, again, back to Tungsten, where there's a lot of work. You actually might have heard it about data sets, where these encoders allow you to sort of more easily take bytes off the wire and turn them into very compact data structures with fewer allocations. OK. So the conclusion is kind of interesting. Data frames came up a lot, which was actually not my original intention. I wasn't trying to secretly sell data frames to you guys. I actually just picked 3 interesting problems with some context needed and tried to describe them and tried to describe the solutions. And it turned out, in all 3 of them, data frames sort of came up. It turned out Python performance problems. Well, skip Python as much as possible. Use data frames. Want to use R and Spark? Well, use data frames. Want more performant primitives? Data frames can provide that as well. And so what we kind of see from this is that data frames or data sets are important for Spark to sort of make progress in, to go further in the areas of expressivity. So getting more than sc.textfile.count to operate in Spark itself, making use of sort of higher level what the user is trying to do. And in performance, which is sort of linked to expressivity, from both knowledge about the data and knowledge about what you're trying to do on the data. So without moving further into this domain, it's pretty hard for Spark to make strides in these 2 areas. OK. So that's all for the main presentation. I actually have a few minutes left over, so let me briefly go over the common pitfalls and leave time for questions. OK. So I'm very quickly over these. Avoid group by key, because the API in RDD requires all values to fit in a single memory, and the data frame group by is implemented correctly. Avoid Cartesian products. Apparently, this is more common than I thought. Always make sure there's a join condition, and you can check with dataframe.explain. If you fail to have a join condition, you'll have a bad time because you'll have an n-squared algorithm, but for sure. Avoid overusing cache. This one may not be so well known. We see people stick cache everywhere. It's the go faster button. Use it everywhere, always. It's very useful. It can be very useful, but people kind of overuse it. So you might try to avoid using it if you explicitly think that the data will not fit in memory or will not be reused. Not that it's a problem it doesn't fit in memory, that won't cause anything to crash. It's just that it won't be useful to you. And it's actually, in 1.6, it'll be worse than useful, less than useful. Anyway, it'll be bad for you because we're going to play an optimization where if you're not using the cache, sort of your shuffles will be faster, will use more space. And so if you start using the cache, even though you aren't actually using it, well, we can't do as much with the shuffle space because we don't know that you're not planning on using it. So consider persisting with memory and disk instead. This sort of avoids having to recompute things, which may be the reason you're caching. But it also means that if memory becomes a problem, you can just stick it in disk. So another common problem with joins is that we see people trying to join small and large tables, which is perfectly reasonable. But the thing is that the broadcast join is by far more efficient than any shuffle-based join. And so if you know that you're in this operation of a small table and a large table, you need to ensure that Spark SQL takes this. So you can use the explain to make sure it is. If you want to try to force it to do so, you can cache the table in memory or use Parquet, because Spark SQL may not know what the size of the smaller table is, so it may not decide to do a broadcast join. And you can also increase, there's a configuration option for the minimum size to do broadcast. You can increase that if you know, oh, my data set is just slightly higher than what Spark SQL by default would broadcast. But when usable, this is an extreme performance improvement. These are some very specific ones. JetSet 1.9. This is it's impossible to find, but the default in Hadoop has inexplicably terrible performance. And even this is only used for S3N, so also avoid S3N entirely if possible. So there's the new S3A available in Hadoop 2.6, but it also happens not to have many. You can actually pull it out and use it in prior versions. It uses the AWS SDK, so you can get some nice features. It also reuses HTTP connections for some speed. But actually, we actually saw something yesterday which made me really intent on killing S3N from our code base, which is that it started buffering it has an if statement that's like, oh, if the response from S3 looks a certain way, read the entire file in memory. And that's pretty scary, because you might not want to read the entire file in memory, especially like in 8 cores in parallel, so we're like getting ooms, because S3 maybe changed the way it responded to some files. And finally, in the RDD API, if you want to do joins and such, you can manually reuse the same partitioner for extra shuffles. We've seen this used a lot, and it's pretty useful. OK, so now time for questions.
Hello? OK, so we actually only have time for one question. Sorry about that. But Aaron does actually have office hours today at the Databricks booth at 5 o'clock today. So where was the hand that was up? Go ahead and please ask your question.
Hi, I had a 2-part question, but I'll turn one just into a suggestion. There's a lot of times where I've seen cache once would be helpful, like where you want to count and then process it. Mm-hmm. So. But the question is related to the S3N versus S3A, and even just old school S3. Amazon now, in their EMR documentation, are saying they renamed the old S3 to S3 block storage or whatever, and they've deprecated both S3N and S3A and are recommending just use S3 for all their URLs. And I noticed recently S3A failed with a lot of network errors. S3N was all right, but then just using S3 was much better. So Amazon, in their latest EMR release, are saying they basically rewrote all the drivers.
So, OK. The thing was, the suggestion was actually to use S3 instead of either of the suggestions, S3 and S3A. I will have to look more into that, but my understanding is in terms of so Amazon does do funny stuff on EMR, where they do give you a different sort of set of HDFS drivers. So if you're doing that, I would do what they recommend. Outside of that, if you're using just plain old Hadoop, S3 is actually not what you want to use, because it's using this funny extra format, which doesn't really play nicely. It's actually like super deprecated. So outside of EMR, I would not recommend using S3, but maybe it is what you need to use, especially if you're using an older version of Hadoop, because it's sort of this like weird block storage thing where it's trying to like play around and do funny stuff.
All right, that's it for questions. Again, we'd like to thank Aaron Davidson for presenting today's awesome presentation. And give us 5 minutes, and we'll be up for the next presentation. Thanks very much.